It is widely known that many species of birds travel huge distances each year as part of seasonal movement between breeding and wintering grounds. Migrating birds share airspace with airplanes, both commercial and military, windmills, and other man-made structures like high-rise buildings. It's important for both the bird's safety and the longevity of these aircraft and structures that we are able to accurately predict when flocks will be migrating and where. We know that birds migrate using cues from the sun and stars, the Earth's magnetic field, as well as mental maps. So why do their migratory routes vary so vastly each year? Why can we not yet easily predict when different flocks of birds will be traveling through different airspace? Well, that's where an exploration of weather patterns becomes so important. While ecologists have traditionally focused on GPS tracking data when studying migratory patterns, it is becoming increasingly important to integrate additional data sources, like weather data. To this end, there arose a need for an efficient architecture allowing ecologists at the University of Amsterdam to access and study a new stream of meteorological radar data. Querying a Postgres relational database just wasn't going to cut it for this task. My name is Allison Walker, and I am privileged to be a participant in the 2019 Summer of HPC program. Over the next 5 minutes, I will describe the project that I have focused on at Surf Sara in Amsterdam, large-scale data techniques for research in ecology. Radars are complicated, both in terms of their technology and the data that they capture. Radar collects information about objects in the surrounding area by using radio waves. The returned echoes can be used to identify aircraft, weather patterns, and even flocks of birds. Every time a radar completes a sweep, a significant amount of metadata and data is captured and stored. Examples of the metadata are radar latitude, longitude, and height, radar elevation angle, the radar's range, the timestamp, and of course, the data itself. Information is captured for up to 16 different metrics each time a radar completes a sweep. All of these data and metadata need to be considered in order to correctly project the data captured into an accurate visualization. Further, meteorological radars capture data in a polar format. Typically, data for visualization is collected and stored in a gridded format, i.e., the position in the matrix represents the position of a pixel. In polar data, however, the dimensions are azimuths, or degrees in a circle, and radius, the distance from the measuring radar station. The complexity and size of radar data means that it's no simple task to filter, process, and visualize, which is basically what ecologists studying these data need to do. So in this project, I developed a data pipeline that could efficiently provide ecologists with access to visualizations for multiple radars around Europe. All the user has to do is input their filters. How did we do it? Let's cover that now. A typical radar might perform a fresh sweep every 15 minutes, meaning 96 sweeps per day. Data collected in each sweep is stored in its own file, in an HDF5 format. HDF5s are hierarchical formats and somewhat complicated to navigate. In building an efficient ETL pipeline for visualizing radar data, a critical first step was to condense these individual files into a simpler format. The many complexities of the radar measurement system meant that it was important that we build a solution that could easily filter and return only the data that the researcher is interested in for their particular question. Parquet was the most sensible format for these purposes. Parquet is a column-oriented data storage format that is efficiently filtered and highly compatible with Spark, the next key tool in this project's toolbox. Once the radar data is formatted into Parquet and saved in Minio, an object storage software, a number of functions for loading, filtering, and visualizing the relevant data were designed. Spark, a general-purpose cluster computing framework, allowed us to seamlessly distribute the compute for these functions across the nodes in our Kubernetes cluster. Next, we used Python and radlib, a Python library for weather radar data processing, to easily generate visualizations like this. To further improve the value of the visualizations, the next step in the pipeline? Georeferencing. Key tools used in this stage were GeoViews, HoloViews, and Xarray. These are all nifty libraries that let us place the visualized radar data exactly where it belongs on the map. Finally, again with the help of Spark, we have this beautiful geo-referenced output. So, there we have it, a functional data pipeline allowing ecologists to query and visualize radar data based on their desired filters. Of course, the final product can be further optimized, but this solution already creates huge efficiencies for the ecologists. Importantly, this was also a great learning opportunity for me to gain experience with data pipelines and data engineering. I've also developed a new fascination with both birds and radar technology. Thank you to both Prace and Surf Sara for this awesome opportunity.